Hi, everyone. I hope you are having a great day. Let me just kick this off with a picture of the beautiful city of Vancouver here. So what you see is the harbor, is the skyline, is the infrastructure. And all of it is alive. Of course, not biologically, but structurally. And it's telling us a story. But we have to just pay attention to understand and to realize the story. Today, I'm going to take you on a journey. I'm going to take you through cities and infrastructures. But more importantly, I want to take you across what I call the architecture of future. My name is Kamyab Zandi, and I'm the CEO and co-founder of TIMEZYX. And what I want all of us to realize and to remember from this talk is that, well, today we are not only facing the problem of building more infrastructure. The more important question that we have to try to address is that the built environment that already have and are in place, how they are going to endure, how they are going to evolve, and how they are going to be prepared for what's coming for them. So let's start again right here at home, the beautiful Lion Gate Bridge. It's an iconic symbol of Vancouver. I'm sure maybe some of you have crossed it this morning, or maybe you have a chance just to go out and have a beautiful view over the bridge. It's been in place for the last 80 years, more than 80 years, since 1938. It's been connecting downtown Vancouver to North Shore. But any infrastructure of this age is facing growing concerns. It's all about the loads that it's carrying, which is much higher than the loads that the designer 80+ years ago were thinking about. It's about the overall aging. It's about the problem of fatigue, the problem of corrosion. But let me just add one even more complex problem on top. And this is the climate change. So today, all of us are experiencing extreme climate events that are happening more frequent. And when they happen, they have higher intensity. So infrastructures that once endured understandable and predictable cycles of weather and temperature now should withstand extreme weather like storms, floods, and extreme temperature changes. Events, once we used to call them once in a century, now are happening every few years. And don't get me wrong, it's not only the problem of resilience. The problem is beyond that. It's the issue of safety, because this impacts lives, impacts economies, and it impacts at some point the public trust. And when we get it wrong, there are devastating consequences. Just go back 2 weeks ago. Down in the US, Midwest, we had a hurricane hitting a really large area, the tornado, actually. And it really changed the setting of that environment. There has been more than 25 lives lost to one single event. And it's not a single event we talk about. Since the turn of the century, there has been more than 500,000 people who lost their lives to extreme climate events globally. But the hard truth is that much of those deaths could have been prevented had we properly prepared for that. Because often, people do not lose their lives directly when they are impacted with extreme wind. They lose their lives when the structures collapse and infrastructure failures. So this talk is really tackling two problems. The problem of extreme climate events that we see happening more often and more frequent, but more importantly, the fact that are we ready for what's coming for our infrastructures? At TIMEZYX, we have a vision. We would like to contribute, along with other industry players, to have sustainable, safe, and resilient built environments on the planet Earth and beyond. And actually, that carries through the name we have chosen for ourselves, TIMEZYX. So time speaks to the ability to foresight. It's really the power to see what's coming. It's the capability to simulate future scenarios and prepare for that. ZYX represents the spatial dimension, all of us, including the built environment, existing. So together, we represent structural intelligence, where it's powered by physics-based models, and it's enhanced with data-driven simulations, and it's actually taking place across the space and time. So we come to work every day with that vision, and we pursue that vision by empowering individuals and organizations to go above and beyond conventional decision-making through the power of advanced technologies. We actually help them to transform from traditional decision-making to the one that counts for a structure itself, helps to understand the structure, monitor it, and protect it for the future. So this is what we work with. We call it a structural digital twin. It's not only a 3D model of your infrastructure. It's a lot more than that. It is a physics-based, real-time simulation of an asset, which is connected with satellite data, which connected through sensor data, and environmental inputs. It provides real-time insight about your infrastructure, how it's going to behave, not only during normal loading conditions, but more importantly, when it's subjected to extreme climate events, before, during, and after such events. And such a model is supposed to evolve as the structure itself evolves, right? Because it's important to understand how the structure works today, but it's more important to prepare what's coming tomorrow. And just like any living organism, now our infrastructure, through the power of a structural digital twin technology, they can also sense their environment, they can compute, and they can respond to their environmental impacts around them. So that's what I want to talk to you about. But the question is, how a structural digital twin, or how an infrastructure itself, understand what it's going through? Today, our infrastructures are monitored 24/7 through a very complex network of sensing technologies. We start from ground-based sensors that collect information from accelerometers and strain gauges, so vibrations and strains and motions. But more importantly, the power of satellite monitoring adds a very scalable and meaningful dimension to this. Because today, we can sense and we can record even smallest movement down to sub-millimeter of the infrastructure, the surrounding it's sitting in, and even the larger context, the entire region or entire country. So the question is, how do we really leverage this huge, massive amount of data when we do our analysis? And I'm going to talk to you about that a little bit today. In one hand, we hear a lot about large language models, right? In short, LLMs. So LLMs are, they do understand and they communicate in human language. But we are working on a new category of simulation architecture, and that is called physics-informed machine learning, which understand and communicate in the language of physical laws, physical systems, right? So LLMs, they understand and communicate in human language, whereas PIMLs, they understand and communicate in the language of physics. The first one is trained on massive amount of data, text data. The second one is trained on massive equations related to physics laws and real-time data. So today, we are building the back end of future structural digital twin based on physics-informed machine learning, PIMLs. And I think we can do something extraordinary. So I'm going to walk you through how a PIML works, but you have to stay with me because we are going back to the basic, the physics 101 now. The spring and mass system, right? You thought you got rid of it during your high school, but no, you have to remember a few things now as well. So if you have a mass and if it's suspended through a spring, your goal is to understand the movement of the mass through time. You want to know if you can predict where the mass is at each given time. So that's the goal. We can, in one approach, we can entirely rely on data-driven approaches, right? So we can really measure where the mass is at any given time. We can have this data. We can feed a machine learning model and then ask it to find patterns. And let's see how it works. It starts with a very poor estimation in the beginning, but as we add to the data points, it corrects itself, and the accuracy improves. But you have to remember, it does not understand the physics. It finds the correlations, it finds the patterns, but the problem is that it does not understand the causation. And that's the problem when we work with conventional machine learning systems for physical infrastructures, right? We need to have large volume of data to approximate behaviors that the system itself, the model itself, is incapable of comprehending. But then we can move to the next approach. So the next one is PIML. That's where we actually incorporate the physics of the problem directly into the analysis. Let's see how it works. It's really accurate right from the beginning. Why? Because we already introduced the physics of the problem, and in this case, the equation of motion. So it does not need to learn the rules. It also knows them. So the physics brings structure, and the data brings context. And that's really the power of PIMLs. But there is one more secret. Let's look at these two simulations side by side. PIML is much faster. It's a few order of magnitude faster than machine learning. And that is really important for real engineering applications. Imagine it's hours leading up to an extreme event and a storm. So you don't have the luxury of waiting. You really need to know how your structure is going to behave. Because as a decision maker, you have to decide whether or not your structure is good enough to be in service, right? So we are building now the back end of a structural digital twin with these systems. And what began as a more of a physics-based model and experimentation, now we scaled that up to full-scale simulations. Now we have developed the capability of having full-scale structural simulation, physics-based, combined with data from satellite and data from ground. And altogether, we can provide real-time estimation. In this particular case, it's a railway bridge subjected to loads from a cargo train twice as much as it's been designed for. So now the owner will know if it's possible to run trains with twice as much loads. But we didn't start this session by talking about loads from train. We talked about extreme climate events. And that's the next thing I wanted to share with you. The same satellite systems that monitor our infrastructure, they also collect information and do forecasting about extreme climate events. Wind intensity, flood, storms, and many other parameters. We can insert this information directly into our structural digital twin, and in real time, we can say where the vulnerable area of the structure is. We can demonstrate if the structure is going to be safe a few hours down the road when the peak hours of the extreme event will be. Or maybe the owner needs to activate an emergency response. So we can really provide a lot of information for fast and informed decisions. So I would like to finish this up by sharing a real example, a real use case. What you're looking at is Kalix Bridge, located in north of Sweden. And it's been in place since 1957, so nearly 70 years. And it's been really a lifeline between very remote communities. It's located in one of Europe's harshest climate environments, very far in the north. And the owner realized back in 2019 that there are a few cracks in a very critical part of that infrastructure, where if you are an engineer looking at such a data, you wouldn't like to believe that there are cracks right above one of the pillars in such a system, right? So we helped them to set up a satellite-based monitoring. Now what you're looking at is the data that has been collected during that time. If I pick a satellite data point off of the bridge, outside of the bridge, you see only seasonal changes. This is the displacement year over year within 5 years, right? It's just seasonal, nothing to be worried about. But if I pick one satellite data point right on top of the bridge, now you see the pattern. About 10 millimeter displacement year over year, adding up to 50 millimeter in total. So the question the owner is now asking themselves is, what does that mean? I know that I have some cracks. I see really the impact of the crack on the displacement, but is the bridge safe today? Or is the bridge safe for future, particularly extreme climate scenarios that they had concern about in this particular location? So we helped them. We got all this satellite drive displacement, and we insert that into structural digital twin, incorporating the crack itself. Now we could show them how the crack is likely to propagate, what the residual capacity is, what is the load-bearing capacity, what is the structural risk altogether, what would be the probability of failure. And this is really instrumental for infrastructure owners as they plan for the future. We didn't only show them the status code, the status report, right? It was the forecasting. It was really the future scenario analysis that helped them. And we didn't stop by looking backwards. We also helped them to look forward. We looked into quite a few extreme climate scenarios and did computations on those, right? What you're looking at is a particular scenario of extreme flood hitting one of the pillars where we had some cracking on the section above. So we could really compute some meaningful load levels, understand what impacts they expect to see, and really plan to properly respond to these extreme events. So by that, I just remind everyone that I started this session by saying that, well, we come to work every day hoping we can contribute to safe, resilient, and sustainable infrastructure. And we do that by relying on and developing systems that are live. So we bring the architecture of Foresight for infrastructure. We enable infrastructure to sense, to compute, and to respond, just like any other living organism on the planet. Thank you very much. Thank you.